So we're going to work with problems of calculating pressure and problems with calculating the force on objects that are submerged. So as you experience when you're swimming, if you go a little bit deeper, the deeper you go, the more pressure you feel. Now that pressure you feel is proportional to the depth. And there's a nice little formula here. First things first, let's keep a couple things straight. Pressure is force per unit area. When you pump up your bike tires or you pump up your car tires, what do you generally pump it up to? I mean, when you fill up your car tires, how much? Yeah, PSI, pounds per square inch. Now, the equivalent of pounds per square inch in the metric system is pascals. 1 PSI is just under 7,000 pascals. So Pascal is kind of a small unit, but it is the unit of force used in the metric system, or excuse me, the unit of pressure in the metric system. Force is just, you know, how much something is pressing or on another object. But when we divide that force by an area, that's when we get, you know, units of pressure. So you can see it right down here. Force divided by area gives you your pressure. Now that force for us, how much force an object feels when it's down at depth, is the density times the coefficient for gravity times the area times the depth. So several things kind of rolled up into one. There is one little bit of a quirk when doing this calculation in the English units. And that quirk is one of our constants, our gravitational constant, is actually kind of built into the density here. So we're not going to have to explicitly multiply by 32 feet per second squared, like we're going to have to do something like that down here with metric units. So again, another little thing that I put in as an aside after we started printing out their handouts is that you don't need to multiply by the gravitational constant when calculating the hydrostatic pressure in the imperial system, that is pounds per square inch, because it's already factored into the density units. So let's see what I mean by all that. So we're going to take a tank 4 feet long, 2 feet wide, 4 feet deep, that's full of water. And we're going to try and find several things about this. First of all, the hydrostatic pressure in pounds per square foot on the bottom of the aquarium. Well, okay. So the pressure for us in this case, let's see, I think I want to write on a separate sheet of paper here. So this is example E. For us in this case, the pressure is just going to be the density times the depth. So, yeah, that's a terrible delta. So this is really a Greek letter delta, at least my awful attempt at that. I think I might want to do that again. All right. Well, that's not much better. A little bit better. So the density of water is given at 62.5. I always thought it was 62.4, but we'll go with what WebAssign is going to use. I think they use this because when you multiply that by 8, you get an even 500. 62.5 pounds per cubic foot times the depth. Well, what's the depth here? Depth is 4 feet. So you're trying to find the hydrostatic pressure at the bottom of the aquarium, and the depth is 4 feet, so times 4 feet. Now I'm doing something that I don't often do, and that is I'm actually keeping track of the units, because I want you to see what's going on with some of these units, because those units and keeping track of them can help make you sense or make sense of whether or not you've got the right thing. I'm going to rewrite that over here, 62.5 pounds per cubic foot times 4 feet over 1. I put the 1 out of convenience. But what I want you to see is this. I've got a unit of feet here that can cancel out with one of them here. How many feet or units am I left with here? 2. And 4 times that's going to be 250. Did units of pounds go anywhere? So this is pounds. What units do I have in the bottom? Feet squared. So this is pounds per square foot. That's a pressure. That's how much pressure is being felt at the bottom of the tank. 250 pounds per square foot. Now, in contrast, let's try and find the force on that. Force is going to be the pressure times the area. So F equals P times A. So the pressure was our 250 pounds per square foot. 250 pounds per square foot. Times the area. Well, let's figure out what the area is. The area is going to be the area of the base. Let's see, it was 4 feet long and 2 feet wide, 4 feet deep. But it's these two dimensions that give us the area of the base. So it's going to be 4 feet times 2 feet. And for convenience, I'll put that over 1. Again, let's kind of keep track of the units. So here I'm going to get 8. 8 times 250, that'll be 2,000. But what's going to happen with the units? Where are those going to go?
Feet squared.
All right, so I'm going to get feet squared here. And then what happens? They cancel. I got feet times feet is feet squared, and that cancels here. So overall, what units am I left with? Good. So 8 times 250 is 2,000 pounds. And pounds is a unit of force. It's like newtons is a unit of force. Yay. Now what's helpful for us here is that this is at a constant depth. But what if you start looking at the sides of the aquarium? Well, then you're no longer dealing at a constant depth. Now it's asked us in our final question, it says find the hydrostatic force on one end of the aquarium. This is a problem you could not do without calculus. It's not something that algebra can handle because the force on one end is changing depending on the depth, and it's changing in a continuous way. So here's our aquarium, and let's see. Let's give ourselves coordinates. I'll put 0 here, 0, 0. Maybe I should put 0, 0 here. I don't think it'll matter. And this would be 0, 4. Let's take a look at the height of a slice. We're going to take a slice parallel to the bottom. And we're going to see how much force is on that one slice. What's the thickness of this slice? dy. So that much is going to be dy. And the width of this slice is just the width of the bottom of the tank, or the side of the tank, and that width was 2 feet. So the force on one slice is going to be a product of the area times the depth times the density. So let's find out the force on one slice. So force is going to be a product of a couple things. The force is going to equal the density, or excuse me, it's going to be the pressure times the area. And the pressure is going to be the density times the depth. Times the depth. Now, I'm not going to make you memorize all kinds of constants like, you know, the density of water or anything like that. So, let's see. That's going to be 62.5 times the depth. Now, the depth in this case, let's see. I guess I can regard it as maybe being the height. That height is going to be a distance of y. You could also do the depth. I think it is going to give you a symmetric integral, but we'll keep it a little bit more user-friendly. So I got 62.5 times y. I need to put in that into the area up here. So this expression is just part of this one here. That's our area.
That's a unit of pressure.
Excuse me, that's our pressure. Let's see, wait. Getting a little twisted around here myself. Pressure times area. Pressure is density times depth. Okay, yeah, so that's our pressure. We got to account for the area here. So let's put that in here. So back to the force then, that's going to be 62.5 times y times the area. Now we need to find the area of this little strip here. Well, the area is just going to be the width times the height. So let's find the area. What's the width? 2. What's the height? dy. So 2 times that's going to give me 125 y dy. That's the force on one slice. Now, you can probably well imagine I don't want it to have just the force on just one slice. I got to add up the force for all such slices. So what's going to do that? What's going to add up the force on all such slices for me? Integral. Good. What should I integrate from and to? 0 to 4. So, James, in a nod to what you were talking about earlier, let me take that 125 and put it out front. Integral from 0 to 4 of y dy, and that's going to be 125 times 0 to 4 of y squared over 2. Which is going to be 125 times 16 over 2 is going to be 8 minus 0, or 1,000. Last but not least, what are the appropriate units of force in the English system? Pounds. That's going to be our unit of force. And make sure that you label your final answer with pounds if you're dealing with the English system. All right. How are we doing with this first one here? Example E? Yes?
Since we already found the pressure, why didn't we use it for and then times by the area?
Since we all here, say again?
I think we already found the pressure. Wasn't it 2
For-
times 50 pounds squared?
That was at the bottom of the tank.
Okay. Oh,
And we're at a variable height. So the pressure is going to change because you're at a different height. Yeah. Appreciate the question. Let's move on to example F. Now, example F is going to get a little bit different because we're dealing with the metric system. So this time we got a tank that's 10 meters long, 4 meters wide, 3 meters high, and contains kerosene with a density of 800 kilograms per cubic meter to a depth of 2.5 meters. We're going to use 9.8 meters per second squared as a constant for gravity. So that's going to be your G. And it's just a little bit annoying that we have to account for that G here, but we didn't really have to explicitly account for it when we were dealing with the first one. So we'll start with the first one. Let's see, our tank is going to be 10 meters by 4 meters by 3 meters, and that last one's going to be the height. And it's
We're doing example F, right?
yeah,
Sorry, it just says I got confused.
that's all right. But importantly, it's filled to a depth of 2.5 meters. So really, it's going to be 2.5 meters is going to be our depth. Let's write down a couple other important things that we need to know. Gravity is 9.8 meters per second squared. And let's see, density of a kerosene is going to be 820 kilograms per meter cubed. Find the hydrostatic pressure in pascals at the bottom of the tank. Okay, so part A, the pressure is going to be the density. I guess I'm using the wrong thing for density. Yeah, that's going to be our density times the constant of gravity times the depth. So it's going to be our 820 kilograms per meter cubed times 9.8 meters per second squared. 9.8 meters per second squared times the depth, and the depth is 2.5 meters. 2.5 meters over 1. Okay, let's see what we get here. Let me take out a calculator for this. Don't feel like doing this in my head. 820 times 9.8 times 2.5 gives me 20,090. And let's play around with the units and see what we're left with. And the units will be a little bit revealing because it'll tell us, you know, how pascals are formed, or what a pascal turns out to be. Let's see, what's going to cancel here? Meters. I got one of them here, one of them here. That's going to cancel and leave me with just units of meters. In fact, what units am I left with, and where am I left with them? Kilogram on top, meters and second squared. So that's 20,090, and a meter per second, or kilogram meter per second squared, is going to be a pascal. So 20,090 pascals. That's the pressure felt at the bottom of the tank. How about the force felt on the bottom of the tank? Well, the force is going to be simply the pressure times what? times the area. And the pressure we can take from this calculation right here. There's our pressure. So I'll start out with that times the area. Area, let's see, so 20,090 pascals times the area. And the area is going to be 10 times 4, so 10 meters times 4 meters. Let's break this down a little bit. That's going to be 20,090, and I'm going to go back to kilograms times meters times seconds squared times 40 meters squared over 1. So it's going to be 803,600. And then units are going to be kilogram meters per second squared. Kilogram meters per second squared, that's a Newton. Okay, so a couple of the ones that don't involve any calculation based on calculus. Let's switch it over to do something that involves calculus, and that is finding the pressure, or excuse me, the force on one end of the tank. So we're going to do the same thing we did with the previous one. That is, we're going to draw ourselves a little tank and calculate the pressure on this one plate, add up the pressure for all these plates moving up. Alright, so part C here. Let's draw ourselves a little tank. And give ourselves a little slice here. So that slice is going to be dy. This time I'm going to put the origin over here, 0, 0. This point is going to have height of 0 and y. I don't think the origin location really matters too much for these early problems. It is going to be something you're going to want to pay attention to later. Let's see, what else things do I need here? Let's find the area of this strip and then calculate the force on that strip. So the area of this strip, well, let's see, how wide is this thing going to be? That was 4 meters wide. So the area of the Jth strip, or just of this strip, I don't need to worry about the Jth strip. We're not setting up an approximation based on Riemann sums, is going to be 4 meters times dy. dy is also measured in meters, so we've got meters squared here technically. Now the height of this thing is y. So let's see if we can't find the force on one plate. Force on one plate or one strip. That's going to be the density times the constant of gravity. So let's see. I'm going to use rho for density. I'm going to try and be more consistent about using rho for density times the constant of gravity times the depth. That's going to be your 820 kilograms per cubic meter times 9.8 meters per second squared times the depth. And what's the depth going to be? 2.5 meters. So let's multiply all those together. I think we already did that, right? We got 20,090. Force on one strip. I think I'm missing one thing here, though. It's going to be the force. It's going to be the pressure times the area. So I need to multiply this by the area. So that's going to be 20,090 times the area, which is going to be 4 dy. And I should have a depth in here. I didn't put the depth in there, did I? No, the depth is, yeah, there's where I made my mistake. The depth is not 2.5 because you were not at a consistent height for all these things. So that depth isn't just 2.5 meters or 4 meters or whatever. That depth is going to be y. Then I need to multiply by the area. So let me fix this. So 820 times 9.8, so 8,036 times y dy. That's going to be the pressure felt, or the force felt on one strip right here. To find the force on all such strips, we need to integrate that from top to bottom. Actually, not top to bottom because this is taller. It's not filled all the way. So we got to integrate up to 2.5. So it's going to be the integral from 0 to 2.5 of 8,036 y dy. Now at this point, I'd be really, really happy if you got this. I'm not interested in you finishing this off, doing it by hand. I would suggest that you would do it by FN int at this point. What we end up with is 100,450 newtons. Yeah, newtons. Now, that's one thing I don't have a really good grasp of is, you know, approximately how much force is a newton. Yeah, it's not something that feels really tangible to me, but then again, I don't work with these problems all that often. All right, but there's our final answer to part C, just over 100,450 newtons. Maybe to get a better feel for that, let me show you a little trick that you can use in your calculator. It's kind of a nice convenient one. You can find it underneath the apps menu if and when this thing ever rolls around. So let me clear out a couple things here. So let's go to the apps menu. And you can follow along with my keystrokes here at the bottom. Go to the apps menu, and then you want to go to side tools, which I think is probably 0. let's see. No, oh yeah, here we go. So on mine, Sci Tools is, doesn't even have a number, goes beyond the numbers. But you should be able to scroll and find this. Gives you a couple nice things that we can do here. Let's press enter again to get past this. Unit converter. That one's pretty cool. Let's go down to unit converter. And you've got all kinds of units that you can convert. So let's go over to number 9, which is pressure. Actually, let's see, let's go back. I don't want pressure, we want force. So let me exit out of that. Let's see, is there force? Yeah, there we go. Force / weight. So that's 8. And we want to convert 100,450 newtons. So now I want to type newtons and turn that to pound-feet. So 2.25 times 10 to the 4th pound-feet. 2.258 times 10 to the 4th. Pound-feet. Or you can write that in regular notation. This is in scientific notation, so I've moved this 5 places to the right, or 4 places to the right. 22,580 pound-feet. It's still not a familiar unit. It just still doesn't ring that familiar to me. But it is a really nice tool for you that you can convert all kinds of stuff. Now, if you want to back up to the main menu, hit the second key and then the quit key. And there you go. You can convert all kinds of things. Let me pause. Questions on that one?
For the force, you said you had to multiply it by area, right?
Yeah, pressure times the area.
So is the area not 4m dy?
Did I forget the 4?
I think you forgot the 4.
Yeah. Yeah, because this was the area. Thank you. 4m dy, so I should have had, let's see, area, depth, 4m dy. Oh my. 4m dy. 4 dy. So that's going to throw everything off by a factor of 4. 4 times that. 4 times that. 4 times that. So 400,000 and let's see, 1,800. 1,800. Yeah, sorry. I hate when that happens. Thank you. There's someone else had one too. No?
Where's the second quit key?
It's the second button and then the mode key. Right above mode, you'll see the word quit. Yeah, so that's how you get out of this. Second quit. You keep on backing out, and then eventually you'll get an exit thing there. So, it's pretty cool. Now, I know this is a math class, but let's dive into a little bit of history. Going all the way back to 1919. And let me pull something up here. In 1919, we were just coming out of World War I. And during World War I, we needed to produce a lot of ammunition, explosives. And that requires a lot of alcohol. And back in the early 20th century, a lot of times they got their alcohol from molasses. So in Boston, they built this huge tank. I mean, huge. 5 stories tall and 90 feet wide. So 50 feet tall, 90 feet wide, and it was full of molasses. Now, molasses, you might be familiar with. It's on maybe a few kitchen shelves. It's a very thick form of sugar, and really thick. For comparison, water has a density of 62.5 pounds per cubic foot. Molasses is something up in the 80s. So let me just double check back here. Let's see, I think I got it as one of these units up here. Yeah, density of molasses, almost 90 pounds per cubic foot. So it's about 50% more dense than water. So it's really, really heavy stuff, and it's generally pretty thick. So let me go back to, where is it? Is it this one? Yeah, this one. And this tank wasn't really well designed. They didn't consult much in terms of architects or engineers. They just built it. And after a while, it started leaking. Right now, you can see it's painted white, but you can see all the streaks there from where it's leaking. People used to go by with buckets and collect some molasses for them to use. They eventually painted it brown just to hide the fact that it was leaking. Now, in early January of 1919, they had just gotten a delivery of some warm molasses from Puerto Rico. It mixed with the colder molasses that was in there, and it started giving off gas. And this thing didn't have a way to vent itself. So the pressure started to build up and build up and build up, and you had an unusually warm day, which contributed to things. What do you think happened? It exploded. It sent a tidal wave of molasses through the streets of Boston, and it was devastating. It was absolutely devastating. The wave was estimated to be moving at 35 miles an hour. It created a vacuum as it passed this one house. It sucked the house into the street, smashed it against a train trestle. 21 people died, about 14 horses died, countless other little critters died. But it was a huge mess. It took them 4 months to clean this thing up. They had to use fire hoses from the ocean and some of their big tugboats and stuff like that to rinse it all out. They didn't find the last of the bodies till like 4 months after this happened. The lawsuit dragged on for 6 years, and it settled at like $600,000 or $800,000. I calculated it was like around $11 million in today's money. They had over 1,000 witnesses. It was a big thing. So I've got some links on D2L if you wanted to look at this further. It's kind of an interesting history. One of the things that surprised me about this was that molasses is what's called a non-Newtonian fluid, so that its properties change when pressure changes. Now, water, is a regular Newtonian fluid. It flows the same way under pressure as it does without pressure. Well, that's not exactly right the way I want to say that, but its properties in terms of how viscous it is and how easily it flows don't change with pressure, but molasses does. And because of that, what happened was it initially flowed like water because it was under a lot of pressure. But as that pressure relieved, and because of the cold day, it slowed down to a real thick paste, and a lot of people that died died because of suffocation. What I'm curious about is how much pressure was on the side of these tanks. So let's figure out how much pressure is on the side of one of those tanks. So we'll do this the same way we did some of the other ones. We're going to work in feet, because that's the way the dimensions are given historically, so we'll work with that. And we're going to look at just a 1 foot slice on this, and then we'll account for the fact that it's It's got a diameter of 45 feet. And then we'll have to multiply by the circumference to figure out just how much pressure is on this. But right now I want to figure out the pressure on one column of this. So we put our 0, 0 down here at the bottom. 0, 0 there. Let's find the pressure on that one column, or that one 1-foot section of this tank. Sample G. So the links I have there, I think there's at least one of them that's a video, and it talks about some of the particulars of what happened. It's pretty interesting. It's only like 10 or 15 minutes long if you're of the mind. So 0, 0, 1 foot wide. Let's calculate the force on one slice. I'll take that slice horizontally. That slice has a thickness of dy. Its depth is y. So force is going to equal the pressure times the area. Let's find the area first. Area of that slice is going to be 1 foot width times the dy height. So really you have units of feet squared there. Let's next find the pressure. So the pressure is going to be the density times the depth. We don't have to worry about that constant of gravity because it's kind of built in someplace. So pressure times the depth, or the density times the depth. Now the density was, what was it, 88.92? I didn't catch that. Let me go back, take a look. 88.92, thank you. So 88.92 times y. Okay. Let's put these two together to find the force on this one plate. Force is going to equal the pressure times the area. So it's going to be 88.92 times y times 1 times dy. You don't need to write the 1. I'm just writing the 1 so you can kind of see where some of these things are coming from. So the force is going to be 88.92 y dy. That's the force on one such plate. Let's figure out the force on all such plates. This tank was 50 feet high. That's really high. That's like twice this section of the building, and then a little bit. That's like a huge tank. So let's integrate this to find the total force on this one foot slice. 0 to 50. 88.92 y dy. And that's not really that bad. I was debating doing fn int, but that's just going to be 0 to 50 of y squared over 2, which is going to be 88.92 times 2500 over 2 minus 0. So basically 1250 times 88.92. Let's do that calculation out. 1250 times 88.92. So 111,150 pounds of force on that 1 foot section of our tank. Now, the question is, how far around was that tank? Keep in mind that it had a radius of 45 feet. So if I want to find the circumference, what's the formula for circumference? 2 pi r. So it's going to be 2 times 45 times pi, 2 times pi times 45, or 90 pi. Let's figure out how far around that is. So 90 pi, 282.743, 282.743. That's going to be feet. If I take that number and I multiply it by my 111,150, 31 million? So take that number, multiply by 30, the circumference, we get 31,426,922 pounds of force. That's a lot. 3 million pounds of force on the walls of that tank. In testimony in the trial, one of the engineers stated that the metal was too thin by 50%. Should have been, I think it said it should have been 50% thicker is what they said. They also use steel. It was also a little bit brittle too, which contributed to the disaster. But there you go. That's a lot of force. Yeah, I think you want to use more than just a small gauge of aluminum for something like that. Okay. Say again?
If we multiply by feet, should we keep those units in our final answer, or should we just leave it as pounds?
I'm just going to leave it as pounds. Pounds is the unit of force for the imperial system. Yeah, I get lost in some of the units here, I'll be honest. I mean, because you got feet here and feet here. The acceleration of gravity is, I think, built into this density somehow. And I won't pretend to understand exactly how all these things work out. So, but I do know that the final answer should be in a unit of force, and that would be pounds. So, yeah, good question. Oh, the dimensions of the tank was that it was 90 feet across, and it was 50 feet tall. So, yeah, the dimensions are, I think they're shown here a little bit. Yeah, you're 280, 90 feet long, that is across, 50 feet tall. So, yeah. So those are the historic dimensions. Any comments on that one? Okay, let's keep rolling with example H. Now with these previous examples, we were kind of lucky in as much as we were you're pretty casual about where you put the 0, 0. All right. You're going to need to come up with a coordinate system that works for you and go with it. So we're working back now with, we're going to work back with metric units again. So a little bit of a little bit of unit whiplash here for us. We're going to submerge a circular plate with radius 7, 2 meters below the surface of water. And we're going to try and find let's see. Let's see. Circular. Express the hydrostatic force against one side of this plate as an integral. So they're really asking you to set this up. You can use FNN to integrate it. It's actually one that you can integrate without even using calculus. Not exactly. So we're not going to have to find antiderivatives and stuff like that. The first thing I would do would be set up my center of this plate. So I'm going to put 0, 0 as the center of this. That way the equation for this is going to be a little bit easier than it might be otherwise. We're going to follow through with what we've done before, and that is take a slice horizontally. We want to try and find the force on that one slice. Force is going to equal the pressure times the area. Pressure is going to equal the density times the depth times the constant of gravity, because we're working back in metric units. Pressure is going to be, let's see what unit do I want to use. I guess I'll stick with density times gravity times the depth. I think they're using something different here. It says assume that the weight density of this water is 1,000 kilograms per meter cubed. Use 9.8 per meters or meters per second squared for the acceleration. Okay. So let's work on a few things here. The biggest thing that we're going to have to struggle with is finding the area here. Now, if this is my center at 0 and 0, what's the equation for a circle of radius 7 centered at the origin? Equals, yeah. So this equation is going to be x squared plus y squared equals 7 squared, or 49. All right, good enough there. Let's see. This is going to be dy. This distance here is going to be a little bit tricky. So if you're starting out from here, some center point along the y-axis, then this distance is going to be x, and this distance is going to be x. In other words, the width, how much is the width going to be? The width is going to be 2x. So if I want to try and find the area, that's going to be 2x times dy. But that dy is telling us something important. dy is telling us that, oh yeah, you better put this in terms of the variable y. We're going to need all this in terms of y. So you're going to have to solve here for y. And when you solve here for y, you get y equals the square root of 49 minus x squared. So the area then becomes 2 times the square root of 49 minus x squared times oops, I screwed this up. I need x as the square root of 49 minus y squared. My bad. So there we go. Now this is all in terms of y, like we need it. All right, so the pressure is going to be the density times gravity times the depth. So let's see. So the pressure density was 1,000 kilograms per cubic meter times gravity, which is 9.8, times the depth. Well, the depth is just going to be your y distance. So the depth will be y. We can clean that up right as 9,800 y. And we're going to have to be careful where y varies. I'm wrong about y. Y has to be the depth is going to be the distance between the surface and this level. So it's going to be 2 minus y. It's going to be top minus bottom. Actually, let me change that up again even further. How deep are we? Let's see. This is going to be a distance of 7, so that'll be the coordinates of 0 and 7. And this is going to be 0 and 9. That's going to be our distance up at the top, our point at the top. So the distance from the surface that our depth is going to be 9 minus y. So that's going to be our final depth. So 9 minus y. And I'm not going to try and cram that in here. So let me just take care of that. That's going to be 9,800 times 9 minus y. That's our pressure. So we can fill in the pressure and the area. There's our area. Here's our pressure. That's going to fill in there. And let me continue this on another page. So the force on one plate is going to equal the pressure times the area. And that's going to give me 9,800 times 9 minus y times 2 times the square root of 49 minus y squared dy. Or cleaning this up a little bit, 19,600 times 9 minus y times the square root of 49 minus y squared dy. Okay. Let's see if we can't find the total pressure on this plate. And there's a couple tricks that we can use in terms of the integration. So if we wanted to try and find the total force on that plate, I would take 19,600. I'll take that out front. I'm going to integrate 9 minus y times the square root of 49 minus y squared dy. But the good question is, what are my limits of integration going to be? Where can I take this slice?
Negative 7 to 7.
-7 to 7. And there's something very nice about that -7 to 7. I'm going to split this up by distributing this and split it up into two integrals. So I'm going to distribute the square root function to both of these terms and then split it up like this. It's going to be 19,600 times the integral from -7 to 7 of 9 times the square root of 49 minus y squared minus 19,600 times the integral from -7 to 7 of y times the square root of 49 minus y squared dy. I think a few of you had me back in Calc 1. And in Calc 1, I made a little bit of noise about stuff like this when you're integrating from -7 to 7. I call that a symmetric interval. And I also gave you a little bit of a heads up, and that is if you have an odd function on a symmetric interval, then that integral becomes very easy. So let's just kind of quickly look at Desmos, and let me pull up an odd function. Y equals x raised to the 1/3 power. That's an odd function. What makes it an odd function? What makes it an odd function is that if you draw in any line y equals m times x, it intersects this graph at symmetric places. But when you're integrating here, try and picture the area between the curve and the x-axis, you know, from say -7 to +7. Those two areas are going to be the same, except one's going to lie above the x-axis and one's going to lie below the x-axis. And when that happens and you add those two areas together, what are you going to get? 0. You get 0 because of the odd function rule. So that's nice. And as far as this part over here is concerned, let's take the 9 out in front. So 9 times 19,600. It's going to be 176,400 times the integral from -7 to 7 of the square root of 49 minus y squared dy. Well, that much, let me just graph that. Let's shut off these. X equals the square root of 49 minus y squared. And let me kind of zoom out a little bit and square this up. What does it look like I got there? Semicircle. Do I need calculus to try and find the area of a semicircle? No. No. It's just going to be 1/2 pi r squared. What's the radius in this case? 7. So that calculation can be replaced by the calculation of its radius, which is going to be 1/2 pi times 7 squared, 176,400, 1/2 times pi times 7 squared. So nice. At least this finishes up a little bit easier. Let's see, this is going to be 49 over 2 times pi. Whew. And I get 13,577,000. 335. And the units in the metric system are newtons. Newtons for force, Pascal for pressure. Whew. All right. Gina.
Instead of integrating from -7 to 7, couldn't you have done 0 to 7 and multiplied it by 2?
Let's take a look here. Yeah, you could have. Yep. Yeah, if you multiply by 2, then if you're multiplying by 2, then you'd have a quarter of a circle. So you compensated for it at the end by doing 1/4 of pi r squared, but you'd already have a factor of 2 out here, so they would cancel each other out. So yeah, that would work out fine. Yeah, good observation. Whew. All right, let's mercifully put that one to bed, or this section to bed.